Hello, everyone. Thank you very much for coming to this presentation. I am Numan Khan from the Department of Electrical Engineering, PIAS, and the co-authors and their affiliations are provided on this slide. Our topic today is on the modular design of a 400 ampere resonant converter-based DC power supply for a plasma torch. Here is an overview of my presentation that will include the introduction, literature review, and the research gap identification, the block diagrams and the requirements of our power supply. And then we will discuss about our proposed design, the results, and the conclusions. So before starting our presentation, here is a brief introduction to a plasma torch. A plasma torch is a device that can be used for the generation of plasma. It is being used in industry extensively for different applications in the medical industry, for the waste management that cannot be done through conventional means, and in the metal shaping that are complex. It acts as a thermal heating source for different applications, and it has two major categories: transferred arc plasma torch and non-transferred one. In the transferred plasma arc, the anode and cathode they are not both inside the body, like in the case of the non-transferred one, where anode and cathode they are both inside the body, and with the help of a working gas, we then force the arc to happen outside the the plasma torch body. Whereas in the case of transferred arc plasma torch, the anode is outside the body of the plasma torch, and the plasma arc that occurs between the cathode and anode. So it is relatively much easy to deal with the transferred arc plasma torch as compared to the non-transferred plasma arc. Here are a few examples of the commercially available plasma torches and their applications. Their ratings vary from 1 megawatt to several tens of megawatts, and their current and voltages ratings from few hundreds of volts in amperes can reach up to thousands of amperes and volts. Their applications are provided over here. So they are in the almost same industry of that metal processings or the complex geometry shaping in medical industry, plasma forming, and so on. It is important to understand what kind of load that we are dealing with. The plasma torch in its cold state, or in the case of perturbations or the transients, it is a highly nonlinear load. Therefore, we require such a design that will ultimately be capable of meeting those requirements, particularly in those conditions. In steady state, it acts as a resistive load and very easy to deal with. But in the case of perturbations, it is important to consider such a solution that will be capable of meeting those requirements. They are discussed in detail in several other articles. Our focus is on developing the topology for such a plasma torch. In literature review, there are different power supplies, such as line frequency based choppers based power supplies. They are extensively used and very popular, but the major disadvantage is that they have poor regulation, and for the sort of load that we are discussing, where it is important to have good voltage regulation at the output and have a fast response, such solutions fail. In addition, we can have multi-phase diodes or thyristor rectifiers with online tap changers and saturable reactors. The issue with them is that they have high current THD, their maintenance cost is high, and they have poor dynamic responses. And due to the inclusion of online tap changer, the bulkiness and the cost and the maintenance is highly increased. There are some other solutions as well, such as hybrid or active rectifiers. There will, of course, be some switching involved at higher frequency. And in the case of rectifier followed by chopper, again, where there will be some hard switching. So these solutions, they are not preferred for our application, because at such high power, the losses will be really high, and they are unable to meet the criteria set by the industry. PWM-based solutions, their responses are really good. They are, they can easily track whatever kind of situation or perturbations come into the system. But due to increased power, the one that we will be working on is in the range of 50 to 60 kilowatt. So for such high power, the power dissipation at such high frequency will be really high, and the overall life expectancy will be reduced as well. Therefore, there are some multi-level converter-based solutions available as well, but they are unsymmetric. The voltage stresses are non-uniform, and sometimes they are not preferred due to these characteristics. And for such high power applications, they are of course not desired. Then we have resonant converters that support soft switching. Therefore, they have increased capability of handling power ratings. And due to the soft switching, the stresses on the semiconductor devices are relieved. And due to soft switching, now we can achieve even further higher frequencies. Hence, the magnetic component sizes will be further reduced. So overall, we have three categories: the conventional methods, where we are using line frequency or the rectifier frequency of 200 hertz, or let's say 300 hertz. They are not capable of meeting the system perturbations for our system. And then we have some high frequency based solutions, PWM inverters, and so on. There, due to hard switching, the losses are really high. They are not desired. And handling of such power by a single module is really difficult. This is what we propose. We propose a resonant converter-based solution where we have input from a AC source. With the help of rectifier and filtering, we achieve DC. Then with the help of resonant inverter, this is included for the soft switching, and furthermore, it can, by changing the frequency of this inverter, we can control our output voltage as well. So it is acting as a regulator in this case. And then we have output rectifier, and then ultimately our load. Here are the specifications of the plasma torch that we are working on. After going through multiple calculations and proposed designs, we ultimately came to this conclusion that modular design is relatively much easy to realize physically. The components ratings are much reduced. Therefore, the system 2 and 3 that includes the resonant converter and the output rectifier and the filtering stage. The multiple copies are being used so that our overall system handling capability is easy for us. Here's the summary of our design for system 1. Then the detailed calculations are given in article. Therefore, I'm just skipping them. Over here, we can see that for the system 2, a comparison is provided for a single unit and modular unit. With the help of modular unit, the current ratings are considerably reduced, almost 1/3. So over here, this is where we see the actual benefit of using a modular design. In some stages, for example, in inductance, apparently it seems that the value of inductance has increased, but the physical size is reduced because we are ignoring the fact that the size varies with the scale of the current. So the current is reduced much, therefore the physical size will be also much lower. So we can see over here that physically when we design it, a much smaller core is required than a single unit. Same sort of analysis is done for the output rectifier. The physical sizes of our output filters are greatly reduced. And since these filters are the bulkiest in the system, therefore it is highly desirable to use this modular structure. And in addition to that, it will be very easy for us to physically realize and test each and every one of them. Here are the results. This is the peak current from the rectifier of 122.5 ampere. The same was discussed and presented in our analytical results. Over here, we can see the ripple. This is allowed by the input inductor. It can be further reduced, but it will add on to increase the cost of the system. So an optimal value of inductor is considered that considerably reduces the distortion in our circuit and also allows a considerable amount of a ripple at the input side. In FFT of the input current, we see that fifth and seventh harmonic are the most dominant. So if we use input AC filters, with the help of that, the overall THD will be reduced. Over here we have our diode currents. The shape is similar to that of the supply current, and the value is same as that of the analytical results. Over here, this is the most interesting. We can see that the soft switching being held in our inverter. This is the main reason that we are using the resonant inverter. Due to the soft switching, the dynamic power losses are much low, and now we can work on much higher frequencies, and we can deal with even higher power levels. Here is the rating of the resonant capacitor. It is important to consider that sometimes in the resonant tanks, the value, depending upon the quality factor, the voltage across this capacitor can increase several times. With our design system and with our calculations, we were expecting 796 volt, and in simulations, the result is very close to that. So our analytical results have been validated through these simulation results. Over here, we can see the output voltage and current, the same of 120 and 400 ampere that we were expecting. At the start, we can see some overshoots that can be suppressed with the help of appropriate controller design that will be considered in the hardware simulations, in the hardware development. These are due to the effect of the different filters in our circuit. Regarding conclusions, due to high efficiency due to the soft switching of our resonant converters, they are highly desirable for such high power applications, and they can help regulate our output voltage as well, even if the perturbations in the system occur. The modular design has been proposed that greatly reduces the component size and ratings. And furthermore, they will be really easy in physical realization and testing. The simulations prove our result, and now we are confident with these results that we can move towards the hardware implementation. Here is the appendix of our calculation and design procedure. The same are given in the article as well. Here are a few references that we have used in our study. Thank you very much for attending this presentation. Any sort of suggestions and discussions are welcomed. You can contact me at this given email address, nomankhan@pias.edu.pk, for further discussions or any sort of feedback. Thank you very much once again.